Good day, my wonderful students of Landmark Tutorial Center. This episode video is actually a lecture on rotation. And today we shall be concentrating much on the rotation of what? Of rigid bodies. Now, as we all know, we are familiar with translational motion. That is motion of a body along a straight path. That's one-dimensional motion. Today we introduce something unique and something new to you, which talks about rotational motion, or the rotational motion of what? Of rigid bodies. Now, there are so many ways you can describe rotational motion of a rigid body. We use some mathematical equations to describe the rotational motion of rigid bodies. And by so doing, we talk about the kinematics and the dynamics of what? Of the rotational motion of rigid bodies. So, today, we're going to be looking at a distinction between translational motion and rotational motion. Of course, a rigid body. What's a rigid body? A rigid body is simply what? It's a body that cannot be easily bent into a different shape. So we have so many rigid bodies. Example of a rigid body is something like a rod, or a wood, or whatever, wooden stick, and the rest of them you can give us examples of rigid bodies. So we shall look at a rigid body can undergo both translational motion and rotational motion. But we're going to be paying attention to what? To the rotational motion of what? Of rigid bodies. So I have on the board rotational dynamics of rigid body. We have defined what a rigid body is, and we shall be looking at some of those parameters or some of the equations of motion that can be used to describe rotational motion. So now, normally, if I am giving something like a rigid body like this, look at this. Let's say I have a rigid body of this shape, all right? For this body to rotate, I must what? I must rotate this body at a particular what? Particular point of rotation, or a particular axis. That is, if maybe I'm giving something like, I have my instructional materials here. Let's assume we have this object. Let's assume this is a rigid body, and I intend to rotate this body. The first thing I have to do is, at what point do you want me to carry out the rotation? I may decide to rotate the body at this particular point. So I bore a hole here. So as I bore a hole, what do I do? Now, this object only has one option. The option it has now is to rotate along this axis, because the axis of rotation I have chosen is the y-axis. So, of course, I cannot rotate this object or this ruler along the y-axis. So I have the choice of choosing whichever axis I want. If I want to rotate the ruler along the x-axis, I may now put my axis like this, and then I can now rotate the object this way. So just assume that this object is just like this ruler we have here. So if I pin this ruler here now, and I bore a hole here, so this ruler now has one option. So you can now see that this ruler can now what? Can now rotate. That's the only option it has. It will rotate along this axis I have chosen. So assuming I have, and I take, this is the axis I'm choosing now. This axis is perpendicular to the board. So if I choose an axis, I say, okay, this body, this object, do whatever thing you wish to do. The only option it has is to what? Is to swing along this axis I have chosen. So now, normal thing, there are so many parameters we can use to describe the motion or the position of this rigid body. Now remember that in a translational motion or motion in one dimension, we can talk about the position of a body by using the parameter which is x. So look at something like translational motion. So we have to produce a dictionary between translational motion and what? And rotational motion. Rotational motion. All right. So in translational motion. So I hope I'm correct with this. Translational motion. Sorry, repetition. So in translational motion, if we want to talk about the position or displacement of a body undergoing motion in one dimension, we simply use the symbol x. X, I talk about the position of the body. And this x now, or the position of that body in one-dimensional motion, the unit of the distance or whatever is given in what? Is given in meters. The standard unit is in meters. Then what is the what? How can we describe the position of a rigid body undergoing rotational motion? What parameter do we use in this case? Of course, in this case, for this body rotating along this axis, what I will simply do, if I want to describe the position, I will simply draw two axes. I can draw two axes along the point of rotation. Remember, please, this is our point of rotation. Point of what? Of rotation. So, of course, this is my y-axis and this is my normal x-axis, as we know. This is our x-axis. So, very simple. If I want to find the position of this rigid body at any given point in time, I can draw a straight line. Maybe I take this line. All right. So, maybe if I have a particle, because we can consider this body as being made up of what? Being made up of infinitesimal what? Masses that build up this object. So assuming I have a particle mass here at this point, we can now say, okay, this mass now, the distance or the position can be shown by taking the angular displacement of that point, of this line, from the what? From the x-axis. So we can call this as our what? Our theta. This theta now is what gives us the position. It tells us the position. Because of course, when you have this ruler like this, of course, if this ruler is here initially, so this is the position. So if we now rotate it now at this point, I can see it has come to a new position. So we can use the angular displacement of this ruler from the initial x position to the what? To this particular point it is, to describe the displacement of the what? Of the body undergoing rotational motion. So in this case, so we have a new parameter, which is theta. The theta is the angular what? The angular displacement. The angular what? Displacement. But in this case, yes, we have given an equivalence of x. An equivalence of x in rotational motion as what? As theta. That is the angular displacement. And of course, we know that this our x, or distance, is measured in meters as the standard unit. The standard unit of what? Of angular displacement has its own unit. The angular displacement is normally given in what? It's normally given in radians. We use radians to measure the angular displacement of a rigid body undergoing rotational motion. Of course, again, now, when we come back to this point, look at this. Of course, this body will keep on moving. So as it keeps on moving, it will be assumed to take or move along a circular what? Circular path. So at a given time, once it is here, it will change its position. And as it changes position, it changes angular, there's a change in angular displacement. So we can call this maybe delta theta. We can call this delta what? Delta theta. So as it moves from this point to this point, it has covered a small arc. It has covered a small what? A small arc, which we can call delta x. This is a small arc because this is a circle. So this small linear distance here is an arc covered. So, but once it changes position, There's a change in angular what? There's a change in what? In the angular displacement, which is given as delta theta. Due to this change in position, or due to this displacement, what caused this displacement? Or this displacement will what? Will induce what we call an angular what? Angular velocity. So of course, another parameter we can use to describe linear motion is what? Is velocity, we know. And velocity, the unit of velocity is normally in what? Meter per what? Meter per seconds. Where velocity is defined as what? As the rate of change of what? Displacement with what? With time. That is dx upon what? Upon dt. So what is the equivalence of velocity in rotational motion? The equivalence of velocity is what? Is our angular what? Angular velocity. And angular velocity in this case will now be equals to what? Will be equals to the rate of change of our angular displacement with respect to what? With respect to time. So, and the unit of angular velocity is what? Is given as what? As because this d theta itself is measured in radians. Time is in seconds. So this now becomes radians. Okay, let's say this is radians per what? Per seconds. Radians per seconds. All right. So of course, and another parameter again we use in describing motion in one dimension is what? Is our acceleration, A. Whereby acceleration is defined as what? As the rate of change of what? Of velocity with respect to what? Time. That is, we talk about the v, the what? The t. So when you measure the rate of change of velocity with what? With time, what you get is called the what? Acceleration, which is measured, the unit is given as what? Meter per second squared. But in terms of what? In terms of rotational motion, our acceleration, that is the angular acceleration, is normally equals to what? The rate of change of the angular velocity with respect to what? Respect to time. Velocity is in radians per seconds. Time is in seconds. So when you combine this, the unit will be what? Radians per what? Per second squared. All right. So there are other parameters we shall also be considering. We shall be considering some other parameters. Now, from this diagram here, there is a relationship because when this body or this particle move from this position to this other position, there is a change in what? Change in what? Angular displacement. And this angular displacement results into what? Into a small linear distance. So there is a relationship between what? Between, okay, of course, if I have this particle at this position, the distance of this particle from the center is equal to the radius of this circle we have here. So assuming this circle now is a circle of radius, let's say r, we want to look at the relationship between our what? Our displacement, the small displacement, and what? And the radius of this small cycle we have here. Very simple. Now, how can we find this relationship? Remember that from mathematics, we are being told that what? That length of arc of a circle is equals to what? Theta over what? Over 360 times what? Times 2 pi what? 2 pi r. Or they can use 2 pi r, small r. So, of course, remember that when you talk about 360 degrees, if you want to convert angles from degrees to radians, angle 360 degrees is always equals to 2 pi in radians. That is, one revolution is equals to what? 360. And 360 is equals to what? 2 pi radians. So this simply means that our displacement is equals to what? Theta over what? You can say 2 pi times what? 2 pi what? 2 pi r. Which that means that this our 2 pi, you can cancel this 2 pi. So therefore, the displacement x will simply be equals to theta what? Theta r. But in this case, what we are referring to from the diagram, we need to find the what? The small displacement, delta x. So therefore, our small displacement, delta x, will simply be equals to our small what? Small angular displacement. Sorry, our length, our small arc, the small arc, please, will be equals to our small angular displacement times what? Times the radius. So this simply gives the relationship between what? Between the length of arc, the length of arc, and the what? And the what? And the radius of the what? Of the cycle taken. So length of arc, small length of arc is equals to small angular displacement times what? Times the radius. So that is a very good one. Now, when a body is undergoing a rotation, it rotates with a particular what? Speed. That speed is always tangential because now here we said that what? That the equivalence of this velocity v, the equivalence of the velocity of a rotational a body undergoing rotation is given as rho, which is angular velocity. That is just a kind of an analogy or an explanation of what? Of v in rotation. But the main speed which a body in undergoing rotational motion normally uses to move around the circular path or whatever path it is spinning is what we call the what? The tangential velocity. Now remember that what? Remember that from this point, okay? Now from here, when the particle moves from this point to this point, it covers a small linear what? Linear displacement. A small linear distance. So that linear distance, delta x, is now given as what? As delta theta times what? Times r. So if you divide both sides by delta t, that will give us that delta x over delta t will simply be equals to delta theta over what? Delta t times what? Times r. So that by the time you now take limits of both sides as delta theta tends to 0, that now gives us that what? We now have that dx upon dt should now be equals to d theta dt times what? Times r. But remember that this dx dt simply means x here stands for what? Displacement, linear, as in linear displacement. So the rate of change of what? Of displacement with time is called what? Is called velocity. But this velocity in this case, we call it the tangential velocity because it is what? It is always tangential to the what? To the circular path of motion. So it therefore means that the tangential velocity v sub t will simply be equals to, now remember here, this dt, d theta dt, is what we call the rate of change of angular displacement with what? With respect to time, which is what? Which is our angular velocity, rho. Then times what we have here is what? Is r. So our tangential velocity is equals to what? Is equals to rho times what? Dot r. So this gives the relationship between the velocity and the what? And the angular, the tangential velocity and the what? And the angular velocity. So this is the main speed which a body uses to undergo or to spin around a given cycle. So all these equations we are actually deriving, we are going to be making use of them as we proceed in our course of studies. As we proceed in our course of studies. So now, the next thing we now do here is to look at the kinematics. We look at the kinematics of what? The kinematics of a body undergoing rotational motion. So we have considered the acceleration. This is what? Yes, we have considered the acceleration. So we now introduce the kinematics of motion. Now, if you can remember,